accurate, complex theory as to how bonding works? No. It's probably pretty much the opposite. The simplest, least accurate method, or a theory to explain how molecules come together, how bonding works. Basically, that's what it is. Lewis dot structure says you make a bond by sharing 2 electrons between 2 atoms. That doesn't tell you anything about how strong the bond is. You might be able to look at it and say it's a double bond, so that's about twice as strong as a single bond. That's about all you can get really from bond strength just from the Lewis dot structure. Does the Lewis dot structure all by itself tell you anything about the shape of the molecule? No, so there's a whole bunch of stuff it doesn't tell you about. Some of what it tells you is wrong. We'll see that as we go along over the next chapter and a half. But on the other hand, even though it's sometimes wrong, it's going to be right most of the time. If it was wrong most of the time, would we bother teaching it to you? Hopefully not, right? So I'm just trying to lead up to something here. So Lewis dot structures, they work 90–95% of the time for what you're trying to get out of them. You just have to realize that there are limitations, and when you run into those limitations, you'll have to go into the more complex ideas that we're going to start getting into over the next week or so. One of those ideas is something called resonance. I asked you to do a Lewis dot structure for sulfur dioxide. If you counted up all the valence electrons, you come up with 18 electrons. Put sulfur in the middle, oxygen's on the outside. So right now I'm halfway through building a Lewis dot structure for sulfur dioxide. Okay, I'm actually about 80% done. I've got all my 18 electrons up there. Got sulfur in the middle. What do I want to check next? Anything look wrong about the way I've drawn it out or incomplete? And you see the sulfur only has 6 electrons around it right now. So I'm at the point, actually step 5, where I'm checking to see if everything has an octet. Sulfur doesn't have an octet. What am I going to have to do here? Make a double bond. Which oxygen do I have to use? Possible trick question. In this case, right now I'm just trying to explain when you might expect to see resonance. If you get a molecule where you need to make a double bond, and you can make a double bond to several different atoms, then that's likely to have resonance. The fact that I can put the double bond here or here, it's not that one's right, the other one's wrong. It's going to turn out, for reasons we'll explain as we try to go along, that they're both equally right, or perhaps equally wrong, depending on how you want to look at it. So I can just arbitrarily take that and make the double bond there. I could just as easily have made the double bond to the bottom oxygen, and that would have been correct as well. These two could be called resonance structures of each other. Show that they're resonance structures of each other, I could use a specific type of arrow. It's not a reaction arrow, because a reaction arrow only goes one way. Not an equilibrium arrow, that's 2 separate arrows, one pointing to the right, one pointing to the left. This is an arrowhead, an arrow with arrowheads on both sides. That's specifically a resonance arrow. What it's saying is that the real molecule is a combination of both of those all the time at the same time. Sort of a weird, complex statement there. But another way to think of it, if I took half a gallon of blue paint, half a gallon of yellow paint, mixed them together, would they flash back and forth between blue and yellow as they sat in the can? Probably not. That'd be unusual paint, right? If I mix blue paint and yellow paint, what do I get? Any ideas? Green paint. Green paint all the time, halfway between all the time. Does that make a little bit of sense what I'm saying there? So this real molecule is halfway in between these structures all of the time. In reality, I'm saying this double bond, half of the double bond is up here, half of the double bond is down here, which sounds weird if I'm talking about one line. How can I have half of a line? How do you draw half a line? If you just draw a skinny line, it's still a line, isn't it? But if we realize that bond is really a cloud of electrons, can I say that I've got half of the cloud on the top half of the molecule, the other half of the cloud on the bottom half? Is that a more reasonable way of explaining how I can have half the bond on top of the molecule, half the bond on the bottom? What we're going to do is combine both of these, or average them together, and the average structure is going to be the real structure. So it's sort of like those two together are equivalent to saying I have got 1.5 bonds from sulfur to the top oxygen, and 1.5 or 1.5 from sulfur to the bottom oxygen, and that's all of the time I have that. Is it kind of difficult to draw half of a bond with a Lewis dot structure? Did G.N. Lewis, who came up with Lewis dot structures, did he bother telling nature that she can't draw half bonds? If nature wants to make half a bond, then nature's going to make half a bond up here, right? Does that seem reasonable? Lewis dot structure is simply the simplest way to draw molecules. If you have the simplest way, isn't it sometimes going to come up a little bit short? To me, I view resonance structures as sort of a patch on one of the flaws in Lewis dot structures. And one of the flaws is Lewis dot structures, you can only draw whole numbers of bonds. You can't draw 1.5 bonds or 1 1/3 bonds, but they can exist. So with Lewis dot structures, 2 electrons shared by 2 atoms, that would be called a localized bond. In other words, the electrons are just stuck in a locality between 2 atoms. Is a localized bond. Something like this could be called a delocalized bond. A delocalized bond is spread over 3 or more atoms. Does that make some sense? And it's pretty logical if you remember that a bond is just an electron cloud. Can I stretch an electron cloud out as far as I want to, pretty much? One way to explain why metal conducts electricity is because that electron cloud stretches from one end of the wire to the other. That's one of the ways of explaining how a piece of metal can conduct electricity. So some of these delocalized bonds can be delocalized over billions or trillions of atoms. But right now we're just talking several atoms at a time. Okay, so again, what we're trying to do at first is be able to look at a molecule and tell if it's going to have resonance. One way, as I mentioned, if you're drawing it and you realize that, hey, I could put the double bond here or here, is that going to be a tip-off that you're going to have resonance? Even just looking at this structure, if I only had this drawing up here, there's something about just this one drawing or that one that would tell me that I could have resonance. If I have, I'll just call it atoms A, B, and C, so 3 atoms in a row, and I have a double bond between a pair of them, and the third one has lone pairs, so that pair has a double bond. The third one has lone pairs. Then I can get resonance. And it also works not only with double bonds, but triple bonds as well. If I had a triple bond there, I could get resonance. Now the way that would work, I've got a lone pair, and I maybe use that lone pair, drop it into between these 2 atoms and make it turn into a double bond. That's what I'm trying to show with the little curved blue arrow, that I'm taking a pair of electrons here, I'm gonna turn it into an additional bond here, make it go from one bond to two. Didn't I already have 8 electrons around the sulfur? Sulfur doesn't always have to follow the octet rule, but in this case it does. So if I already have 8, if I move 2 more towards it, which is what I'm doing with the blue arrow here, I'm gonna have to get rid of one of the bonds there. That's why it has to be a double or a triple bond, because I can get rid of one of them, and still have a bond holding it together. I'm gonna push this pair of electrons up to a lone pair here. So that top little blue looping arrow, that becomes that pair of electrons. This one down here, I'm saying it turns into that second bond there. So I'm just talking about 2 different ways to spot something's gonna have resonance. Okay, some sense? Okay, why would molecules want to have resonance? Is that probably making the molecules more stable or less stable to have this idea of resonance happening? More stable. If it was making it less stable, it wouldn't happen. Does that sound true of nature? Nature wants to make things more stable. Okay. If I had this just a double bond up here and didn't delocalize it, didn't spread it out, wouldn't I have 4 electrons crowded around this space? Would that be a lot of electron-electron repulsion? Double bond, that's 4 electrons. That's what I'm saying, there's 4 electrons crowded in one space. If I take that pair and spread it over here, would that reduce the amount of electron-electron repulsion? So if I more evenly spread the electrons out over the molecule, that reduces electron-electron repulsion. Does this molecule perhaps have formal charges? That's something we talked about earlier this week. Do the oxygens have the normal number of bonds? One of them doesn't, right? One's a double bond, that's normal. With the single bonded oxygen, that's got less bonds than normal. So, is it possible this one has a formal charge on it? Can you look at it and figure out what it would be yet? -1 oxygen with 1 bond, 3 lone pairs is going to be a -1, because you're going to take 6, the valence electrons for a neutral oxygen atom, group number, minus the number of bonds, -1, minus the number of lone pair electrons, so 6 minus 1 minus 6. So whenever you see an oxygen with 1 bond, 3 lone pairs, it'll be -1. That oxygen will be 0. The whole thing really is a neutral molecule. Do I need to do the math on sulfur, or can you tell me what sulfur must be? +1, because it has to add up to 0. To go through and do the math, hopefully we'd come up with a +1 for the sulfur. Here, still +1 there, -1 here, 0. When I average everything out, sulfur is still +1. What I'm going to do is add these together. So in both of them, sulfur is +1. So on average, sulfur is always +1. This is just an average drawing, trying to explain what the real molecule looks like. If the negative charge is here half the time, the other half of it neutral, on average, what's halfway between 0 and -1? -1/2, does that make some sense? Is this resonance perhaps going to allow me to spread out that formal charge? Again, if I spread the electrons out, might that stabilize them? And hopefully what I had said earlier makes sense too if I talk about the formal charges being more evenly spread out. Would it be more stable to have half the negative charge on one oxygen, half the negative charge on the other, rather than concentrated on just one? I'm just trying to illustrate why resonance, why the delocalized bonds would make for a more stable molecule.
Are we ever going to be asked to represent it that way?
Not really, but it's helpful to think about it that way. What I might be asking you to do sometimes is particularly something called bond order. A single bond has a bond order of 1. In other words, 1 bond, bond order equals 1. Bond order just means how many bonds are there. Double bond is a bond order of how much? 2. Bond order 3 is triple bond. what would the actual or real bond order be here? 1.5? So, another way of saying it's 1.5 bonds is to say that the bond order equals 1.5. Could I maybe ask you which is stronger? A sulfur-oxygen single bond, sulfur-oxygen double bond, or the sulfur-oxygen bond in this one molecule? If I asked you to rank those from strongest to weakest, which would be stronger, a single bond or a double bond, just in general?
Double bond.
Double bond, so if I was talking a true sulfur-oxygen double bond, it would be the strongest of those three. If it was a sulfur-oxygen single bond, it'd be the weakest of the three, and one at the 1.5 fits somewhere in between. If the double bond is the strongest, might it also be a shorter bond? We can talk about bond length, how far apart the atoms are in a bond. Wouldn't a stronger bond pull the atoms closer together? So, if I was talking about bond order, some things I do as questions on tests. You know, you have to go through, draw the resonance structures, figure out the bond order, and then maybe you have to rank things from strongest to weakest, or shortest to longest bonds. Are we ready for something that involved, or do we need to do some simple ones first? Try some simple ones first, and then try something like that? Probably the best approach. Okay, in this case we had two resonance structures. These were the resonance structures. This is just me, and some books use this format to try and get the idea across of what we mean by an average structure. Not all books use that sort of a drawing. In this case, it was two resonance structures, but it's not always going to be two resonance structures. Carbonate is going to have resonance structures. I'm telling you that up front, otherwise why would I be talking about it now? Should I maybe let you try and draw a Lewis-Strauss structure for carbonate, and then try to do something in terms of coming up with resonance structures for it? Figure out how many there are going to be.